Today we'll transition from talking about machine learning models to talking about Bayesian statistics and related techniques. Let's jump straight into this with an example. So suppose you have a coin that an acquaintance is about to flip, and you need to come up with a single number to represent the heads probability of that coin. The typical answer here would of course be a half. However, we might choose to be a little more nuanced about that. We might want to say, well, it might not be exactly a half, it's probably very close to a half, but also there's some probability that it's 1 or 0 if the coin is double-headed or double-tailed. And it could even be between a half and 1 or between 0 and a half if it's weighted to one side or the other. So we might choose to draw a probability distribution that looks something like that. So we call this distribution our prior, or our Bayesian prior. And conceptually, what's going to happen is that if we see the coin flipped repeatedly, we'll be able to collect that data as evidence to update our prior. So for example, if we saw the coin flipped 10,000 times and we saw 7,500 heads in those 10,000 flips, then we would be very strongly inclined to think that the heads probability of the coin was actually very close to 3/4. Because if the probability were different, like a half or even 0.6 or 0.8, it would be very unlikely to get roughly 7,500 heads. And if we wanted, we could quantify that more precisely using the central limit theorem. So this new distribution, updated from the prior based on the evidence that we observe, is called the posterior distribution. So we'll call our parameter p theta so that we can write this equation down using the customary variables, with theta representing model parameters and x representing collected data. And this letter f represents the distribution of the parameters. So maybe f sub capital theta of theta is how you would write this in a bit more long-winded way. But we want to keep the notation relatively clean, and in practice it's not too confusing to tell these 4 different f's apart. They do mean 4 different things, but you can tell which one is which based on what you see in the parentheses. So in its most basic form, this is just Bayes' theorem for densities, but we're going to interpret each of these terms in light of the Bayesian statistics framework, where we have a prior distribution, observed data, and then an updated posterior distribution. So we begin with f of theta, that's our prior, and what we get out of the calculation is our posterior. And the factor in the denominator, which represents the marginal distribution of the data evaluated at the observed data, we'll be able to ignore because it doesn't depend on theta. It's just like if I said I have a probability density that's proportional to x squared on the unit interval. That specifies the density because you can work out that the integral of x squared over the unit interval is 1/3, and therefore the constant out front would be 3. So you know the density is 3x squared. Same idea here. And finally, this factor written in green is a quantity we've looked at before. It's the density function for x evaluated at the observed value of x. That's called the likelihood. So looking back up at the picture at the top, the way we get from the red curve to the blue curve is just by multiplying by the likelihood. And the probability of seeing 7,500 heads out of 10,000 flips is not actually very different if we assume a probability of 0.49 or 0.51. So the likelihood function is quite flat in this region. It's very, very small, but it doesn't vary that much as you adjust theta a little bit. So what we would actually see here in this graph is a very small bump right there, which is sort of a vestige of our prior distribution having a spike at that point. And similarly, the likelihood for p-values very close to 1 or very close to 0 are going to be extremely small, and so our probability density there gets squished way down. But this is the mantra you really want to nail down. Posterior is proportional to likelihood times prior. So in this problem, we'll change gears slightly and think about a particular distribution that we haven't looked at before. This is called the beta distribution. And the main takeaway is that it's just proportional to p to some power times 1 minus p to some other power. And those powers can be whatever you want. We happen to call them alpha minus 1 and beta minus 1, where alpha and beta are parameters we're going to be able to adjust. And the minus 1's there just for convenience. And then we have this beta function in the denominator, and that's just defined to be whatever it has to be for this whole thing to integrate up to 1. So the beta function evaluated at a particular alpha comma beta pair is just going to be the integral from 0 to 1 of this function. So the first prompt is to just plot this beta function for a variety of different choices for alpha and beta and experiment. What happens when we try large alpha and beta? What happens when they're small? What if one is bigger than the other? So when alpha and beta are both 50, we get this distribution, which looks quite a lot like a normal distribution, although it's not a normal distribution, of course, because it's 0 outside the interval from 0 to 1. And if we move alpha and beta up quite a bit, and preserve their equality, then we get another bell-shaped distribution but with a smaller standard deviation this time. If the numbers are quite low, same idea, just spreads out quite a bit more. And if the numbers are all the way down to 1, then we get an exponent of 0 on both the p factor and the 1 minus p factor. So we just get a constant density of 1. This is sometimes called an uninformative prior. The idea being you don't want to commit too much to one p-value or another, so you just take something nice and flat as your starting prior. Notice too that if beta is quite small and alpha is quite large, we end up shifted very far to the right. And that's because we'll have a p to the alpha factor involved, which is going to give a very, very small result for all of these p-values. And 1 minus p to the beta isn't smashing down the output values nearly as much for values of p that are close to 1. So we end up with a maximum over quite close to 1. And in fact, if we lower beta enough, we can actually get a non-zero density value even at 1. So in problem 3, we'll tie these two threads together. We talked about the beta distribution, which is just a probability distribution, and we also talked about Bayesian statistics, where we have a prior distribution, we make observations, and then we update our prior to get a posterior that incorporates the evidence contained in those data. And as we said, posterior is proportional to likelihood times prior. That's how we're required mathematically to perform these updates. So what we're going to do is see what happens when our prior distribution is a beta distribution for the coin flip problem. And what ends up happening is pretty cool. So the prior is proportional to p to the alpha minus 1 times 1 minus p to the beta minus 1. And the likelihood is the probability mass function evaluated at the data we actually observe, conditioned on p, or conditioned on theta. In other words, we get to fix p for purposes of making this calculation. And we ask, what's the probability mass function at the particular observed sequence of heads and tails that we got? So like if we got heads, heads, tails, tails, heads, then we would get a factor of p for the first head, then another factor of p for the second head, then a couple of factors of 1 minus p for those two tails, and then another factor of p for that fifth head. So we can summarize this by saying p to the number of heads, which we can call, let's say, capital H, and 1 minus p to the number of tails, which we can call capital T. So h and t are just functions of the observed data, so we'll know their values whenever we see the data. And that means that the posterior, which is proportional to likelihood times prior, is proportional to p to the h, 1 minus p to the t, times p to the alpha minus 1, 1 minus p to the beta minus 1. And that works out to another beta distribution with the alpha and beta values just incremented by h and t. So that gives us a really nice interpretation for the parameters of the beta distribution. It's like if we started with an uninformed prior and we observe a certain number of heads and a certain number of tails, that's telling us directly what the alpha and beta values are going to be for the posterior distribution. So in problem 4, we'll have this kind of cutesy setting of a wingnut factory, which from past history, you believe manufactures non-defective wingnuts with a probability that's beta distributed with parameters 80 and 3. But then you get a dozen wingnuts from the factory and half of them turn out to be defective. So the question is, how does this update our beliefs about the factory's non-defectiveness probability? And also, how can we boil that down instead of describing it as a full distribution to just a number or maybe an interval, analogous to a confidence interval from frequentist statistics? So first, we just learned how to update a beta prior in light of new evidence. We just increment the alpha and beta values. So previously, our alpha and beta values were at 80 and 3. So our distribution looked like this. We're very confident that the non-defectiveness probability is quite high. But then when we see 6 more defective wingnuts, beta gets incremented to 9. But we also saw 6 more non-defective wingnuts, so alpha gets incremented to 86. So this is what our distribution looks like now. And one handy thing about Bayesian analysis is that because we're describing the model parameters with a distribution, we can boil that distribution down to a number or an interval in the standard ways that we do that for a distribution. For example, we can find the mean to come up with a single Bayesian point estimate of this probability. And we can also compute quantiles of this distribution, let's say trap 95% of the probability mass with 2.5 to the left and 2.5 to the right to come up with a 95%. I'm tempted to say confidence interval. Many people feel that the term confidence interval is very closely wedded to frequentist reasoning, and so they use different names for this interval when you're doing Bayesian statistics, such as a Bayesian credibility interval or a Bayesian posterior interval. But in any case, we can get that value just by computing quantiles of this distribution. So we get a point estimate of 0.905 and a 95% posterior interval of 0.839 up to 0.955. So part B says, critique this analysis. Why might you be more skeptical of the wing nut factory than this calculation would suggest? And I think the key assumption you would call into question in a real-world version of this is the IID assumption. So underlying both frequentist and Bayesian statistics is the idea that the observations that we're getting are from the same distribution and they're independent of one another. Whereas a manufacturing process has time as really a crucial component. If there were many recent failures, that's probably an indication of some recent changes that had some adverse effects. So you would update your beliefs in a way that's really different than you would if, for example, you were flipping a coin repeatedly where you can see that the coin is the same, you expect its behavior is not changing at all over time. So in problem 5, we'll begin to set up the question that drives a lot of applied Bayesian statistics, which is what do you do when you're not in a conjugate prior situation? So beta distributions, for example, aren't fully expressive. You might have a strong commitment to a prior that's not in that family. Or maybe for a given problem, a family of conjugate priors is not available. And what we'll see is that this ends up being quite a computationally intensive task, although in many cases modern computers are really up to it in ways that they mostly weren't several decades ago. So suppose we have a prior which is proportional to log of theta on the interval from 1 to 2. So let's just plot that. So it looks something like this. So we believe it's more likely to be over at this edge than this edge, but we have a positive density that gets down to 0 only at the left edge. So this parameter is representing the mean of our data. For this example, we'll assume that our data are coming from a normal distribution with that mean. So for example, it might be centered at 1.4, in which case it looks something like this. Or if p ended up being closer to 1, then it would be shifted to the left a bit, closer to 2 would be shifted to the right, and so on. So in part B, we're asked to come up with a formula for the posterior mean, and note that it's an integral that we don't know how to compute analytically. So posterior is proportional to likelihood times prior, and ignoring constants, we get a factor of log theta from the prior density, and a factor of e to the minus x minus theta squared over 2 for the likelihood. So that's just for simplicity assuming we see a single value x coming from this distribution. So to turn this into a density, we need to divide it by its integral over the interval from 0 to 1. And then to compute the mean, we need to multiply that density by theta and integrate. So this part is the posterior density, and we've taken the liberty of separating that denominator out from the integral. And neither of these integrals are we going to be able to perform exactly using analytic techniques. If you want some extra confidence of that, you can put them into SymPy or Wolfram Alpha and see that they don't come up with anything good. So problem 6 asks, how could we evaluate those integrals in a way that's efficient and accurate? And also, why would that approach not work if we were working in very high dimensions instead of the number line? So the answer to the first part is we can just use standard numerical quadrature techniques, numerical integration techniques, things like the trapezoid rule or just an ordinary Riemann sum. And then why wouldn't that work if the data were high dimensional? Really, the point is that it becomes exponentially difficult to densely sample your domain as the dimension of the domain goes up. So like if you have an interval and you want to have at least 1 point in each half of the interval, you can do that with just 2 points. And even though that's hardly a dense sampling of the interval, let's run with it. For a square, if you want a point in each quadrant, that requires 4 points. And likewise with a cube, to have a point in each octant requires 8 points. So even in a 100-dimensional space, it would require 2 to the 100 points just to achieve this very sparse sampling. And even observing the value of a function at that many points, we probably won't be able to estimate its integral very accurately. We're going to return to this idea, and it's going to be the foundation for large swaths of modern Bayesian analysis. But before we do that, let's set up a tool that we're going to use to solve it. So we'll start in this very simple scenario where we have 4 points, A, B, C, and D. And we're going to imagine a particle performing a random walk on this set of 4 points. So for example, the random walk might start at B, and it will see 2 arrows pointing out from B, each labeled with 1/2. So that means it's going to choose with probability 1/2 to go to C, or with probability 1/2 to go to A. Then once it gets to its new location, let's say it happened to go to C, it's going to just repeat that process. It sees a 1/2 loop, meaning that it should stay at C for the next move with probability 1/2. And also there's a 1/2 probability that it transitions to D. So let's say it chooses the right step again and it goes to D. Now D has only 1 arrow going out. It's labeled with a 1, so that means with probability 1 from D on the next step, we're going to journey to A. So this random process is called a Markov chain, and the term Markov there refers to the fact that we're making decisions about how to jump based only on our current location. We're not keeping track of any back history, doing things like saying the 6th time you visit B, definitely go to the right that time. Every time you visit B, it's 1/2 probability to the left, 1/2 to the right. And the way we'll describe a Markov chain is with something called the transition matrix. So this is the matrix whose ijth entry gives us the transition probability, the label in this figure, from node I to node J. So for example, this 1/2 is telling us that the 2, 1 entry should be 1/2. So this is what the transition matrix looks like for this Markov chain. Now, in part B, we want to simulate 10,000 runs of this process carried out for 100 steps each, starting from A. So we'll start from A, we'll take 100 steps according to these rules, and we'll see where we end up. And then we'll do that 10,000 times. And then we'll repeat that whole process, but starting from B. And what we want to look at is where we are at step 100 and how it changes depending on whether we start at A or start at B. And I'll give you a moment to think about what you would expect out of this. Does it seem like it should matter whether you started at A or started at B after you've taken 100 steps? We'll start by defining a function called takeStep, which starts from a particular node I, which might be 1, 2, 3, or 4, and then it chooses the next node based on that particular row of the transition matrix. So we'll sample from 1 to 4 with weights given by those entries of P. So for example, if we take a step from 1, we step to 2 sometimes, other times we step to 1, we never step to 3 or 4 because there's not an arrow connecting 1 to either 3 or 4. Now let's define a function which actually performs this random walk. We'll call it chain, and it needs a starting node and then a number of steps to take. So we'll let X be our current node. We'll start it at start, and then we'll repeat this process of taking a step. We'll take a step from where we are, and that will be our new state. So we'll assign that to the variable X. And we could keep up with our whole history, but that won't be necessary here because we just want to know where we end up after n steps. Okay, so let's make a couple of histograms. We'll start from 1 and take 100 steps, and we'll do that 10,000 times. And then we'll start from 2 and take 100 steps and repeat that 10,000 times. And what we'll see, as perhaps you initially suspected, is that each of these 4 locations has a value which expresses about how much time the random walker spends at that point in the long run. And it really doesn't matter where you start. After 100 steps, the probability that you're at 4 is 1/9. The probability you're at 3 and at 2 are 2/9 each, and the probability you're at 1 is 4/9. That's true whether you start at 1 or whether you start at 2. It would be the same idea if we started at 3 or 4. And incidentally, one way you can prove the result that these two distributions are going to be very close to each other and will converge to the same limit as this value 100 goes to infinity is to imagine 2 different walkers, one starting at A and one starting at B, and they're going to take their steps in tandem. And they proceed independently until they happen to hit the same node at the same time. And then after that, they'll move in lockstep with one another. So they're going to track the same randomness and make all of the same steps after that. So conceptually, you can see it's very likely that at some point they'll cross paths, and then at the 100th step they'll have to be at the same location. So the only discrepancy in probability for, let's say, being at node C on the 100th step would have to come from the very unlikely event that the 2 walkers manage to avoid one another for 100 steps. So in part C, we'll begin to access another computational tool for exploring the same idea. So we're asked to show that the ijth entry of P to the n gives us the probability that we're in state J if we started from state I and then took n steps. So let's start by thinking about what happens if we compute, let's say, the 3rd row first column entry of just P squared. So multiply P by P. What does that correspond to? Well, we dot the 3rd row of P with the first column of P. 0 times 1/2 plus 0 times 1/2 plus 1/2 times 0 plus 1/2 times 1. And if we look back at the diagram, what we'll see is that those products correspond to the probability of moving from node 3 to node 1 along each possible path. For example, the probability of moving C to B to A is equal to 0 times 1/2, or from C to A, it's going to be 0 times 1/2. Both of those are 0. Then from C to A is going to be 1/2 times 0. And lastly, from C to D to A is going to be 1/2 times 1, and that's equal to a half, and that gives us the total contribution. But the takeaway is that this matrix multiplication operation, performing these dot products, which sum these pairwise products of probabilities, just organizes this process that we could carry out directly on the diagram, which says, what's the probability of going from one node to another in 2 steps? Well, it's the sum over all possible intermediate nodes of the probability of getting there through that intermediate node. And then going from p squared to p cubed is the same idea. If we want to know the probability of getting from C to A in 3 steps, we can compute the probabilities of getting to each of the other nodes in 2 steps, and then multiply each of those probabilities by the transition to A and sum. So the bottom line is that the entries of p to the n give us the probability that we're going to be in a given state given each starting state. So with that in mind, we can calculate a value like p to the 100, and what we would expect to see based on these histograms is that the rows will be the same. And that checks out. So technically they're not exactly the same, but within machine precision they're the same as 4 nights, 2 nights, 2 nights, and 1 night. So conceptually what's happening is that because of the way the arrows are structured with lots of things feeding into A, it tends to spend more time at A, and every so often it gets to D, but then when it gets to D it moves back very far away from D and it takes time to get back over there. So it spends less time at D and more time at A. If we want to visualize a particular trajectory, we could just keep track here. So we get something like this. It tends to spend more time at the bottom, and then once it starts moving up, it tends to get up to D and come back. So in part E, we'll look at yet another way to get the stationary distribution, which is to compute the spectrum of P transpose. So we'll look for the eigenvectors, and specifically we'll look for the one which corresponds to an eigenvalue of 1. So if we transpose P, we get an adjoint, and for some reason eigen is not prepared to hit adjoints. So we can do this trick of copying P transpose to get an ordinary array, and then we can call eigen on that. So we get this eigenvalue of 1, together with maybe some complex eigenvalues, and then there's another real eigenvalue here, but it's less than 1. And so this is in the 4th position, so the 4th column is going to be the eigenvector corresponding to that eigenvalue. And we see that indeed these middle 2 terms are twice as big as the last one, and the first one is twice as big as each of those. And these values don't match the 4 nights, 2 nights, 2 nights, 1 night that we saw above, but that's just because of how they're normalized. They're normalized to have an L2 norm of 1 rather than an L1 norm of 1. In other words, the square root of the sum of their squares is 1 rather than the sum of the actual values being 1. So in summary, Bayesian statistics treats model parameters as random variables with a prior distribution that are updated to get posterior distributions by multiplying by the likelihood. Conjugate priors are prior distributions with the property that they update under multiplication by likelihood to give other distributions which are still in the same family. And this is convenient because it makes updates very easy. Lastly, we talked about Markov chains, which are random walks that follow specified transition rules. The transition matrix of a random walk is the matrix whose ijth entry records the probability of transitioning to state j, given that you're in state I on a particular step. More generally, p to the n has the property that its ijth entry is the probability, given that you start from state I, that you'll be in state j after n steps. Lastly, the stationary distribution is what you get in each row of p to the n when n is large, and it's also the eigenvector of p transpose corresponding to an eigenvalue of 1.